I assume you're happy recording now, no?
Yeah, that's fine.
Okay, everyone, welcome to the latest of the DARA e-seminar series. We're now up to double figures. This is number 10. So we've had a good run over the summer now and into the winter here in the north. Good to see many familiar names coming back for this one as well. So it's a real pleasure today to introduce Professor Anna Scaife, who will need no introduction to many of you as being a great friend and leader within the DARA family. Obviously, leading the DARA big data project out of the University of Manchester. So Anna started her career in a PhD at the University of Cambridge before moving around over to Dublin at the Institute of Advanced Study there, before then having a staff position at University of Southampton, and then finally moving to Manchester, which, as we know, is a real sort of powerhouse for world radio astronomy, and has been there ever since, and going from strength to strength. So today Anna's going to be talking about her favorite subject, really, I guess, of sort of, big data, AI, etc., and its role in astronomy and wider science, really, and also introducing the topic of bias as well. So, as usual, if you have questions as you listen to the talk, then please just pop them in the Q&A box, and then we'll save them till the end of the talk, and then get you to come on and ask your questions. Okay, so over to you, Anna. Take it away.
Okay, thank you very much, Melvin, for the kind introduction and the invitation to talk today. It's a pleasure to talk to DARA. And I'm going to be talking about a subject which I think is quite familiar to a lot of people, which is, of course, radio astronomy and the SKA. And for just a quick intro for anyone who's not familiar with the SKA, it is, of course, two telescopes. The first of which is going to be sited in southern Africa and centered in the Karoo in the northern Cape of South Africa, but then ultimately with dishes stretching across sub-Saharan Africa, all the way across to Madagascar and out to Mauritius. And this is an artist's impression of what those dishes might look like. But of course, there's also a second component to the SKA, which is the low frequency component, so quite a different beast in terms of the technology that goes on the ground. And that's going into Western Australia to Murchison Shire, because for the low frequency astronomy, you need an even more RFI quiet environment than you find in the Northern Cape. So one of the things that I like to talk about when I talk about radio quiet areas is population density. And in Murchison Shire in Western Australia, the area covered is about 50,000 square kilometres, which is about the same size as the Netherlands, but with a population of 110 people. So it's pretty much as low as you can go in terms of population density. Now, of course, with all these antennas on the ground, and there are going to be 130,000 of these dipoles in Western Australia, 197 dishes in Southern Africa for phase 1 of the SKA. The other thing we have to remember is that there's going to be a huge amount of data produced by the telescope. And anyone who's familiar with interferometers knows that it's not just the number of antennas that we produce data from, but the number of antennas squared for the visibility data. So in fact, the data rate is huge and needs to be processed in multiple stages before the final data products are then shipped around the world to all of the waiting astronomers who are eager to do their new research with the SKA. So I think that although we often think of the SKA as, a giant scientific facility, we think about it in terms of the radio astronomy and the science goals, and that it's important because it is designed to answer the most important questions in modern astrophysics. The other thing that we can't forget is that it's also a big data machine. And it's not only a big data machine, you know, in potentia in the future when it comes online in about 2027, the full array, but in fact, the components of the SKA are already taking data. So this is the Meerkat telescope in the bottom image. 64 dishes of the Meerkat telescope are already on the ground and operational. They're already taking data. They will be integrated into the 197 dishes of the SKA1 mid. But Meerkat tells you something else that's really important about interferometers, which is that you don't need the whole thing to be working to start using it, which is that every time you put a new dish on the ground, you get a new set of baselines and you can start using those data even before the full number of dishes are ready. So although we talk about the SKA in the future, it's also true to say that it's already a big data machine, and anyone who's been dealing with Meerkat data sets already will be aware of that. So to put that into context, when the SKA comes online fully in 2027 for first science operations, the data products that are going to be shipped around the world, so not the raw data rate out of the telescope, but actually the compressed data products, are going to produce about 600 petabytes of data per year. So that's 300 petabytes from each of the telescopes, 300 petabytes from Southern Africa, 300 petabytes from Australia. And to give you some comparisons, that's big not only in terms of other science experiments, but also in terms of commercial data rates. So if you look at things like uploads to Facebook or searches on Google, those are sort of in the hundreds of petabytes per year range. The other one I get asked about quite regularly is Twitter. Twitter has an immense data rate of about 8 terabytes per year, which is so small it would just be a speck on this plot. In terms of scientific instruments, the largest radio astronomy archive at the moment is the LOFAR telescope, which is growing at about 25 petabytes per year. And even the LHC, the 5 big experiments at CERN, are only producing about 73 petabytes per year. Although this is a slightly disingenuous plot to the particle physicists, because by 2027, CERN will also be producing about 300 petabytes a year. Now, even though that 600 petabytes is really big, it's nothing compared to the raw data rate of the telescope. If you stored all of the raw data out of the SKA low, you'd be storing 5 zettabytes of data a year. And I genuinely think that the only people I've heard stand up at computing conferences and say the word zettabyte with complete confidence are radio astronomers at this point. And I'm guessing that some people will be thinking, what's a zettabyte, right? Because we're quite happy with terabytes and probably even petabytes. But yeah, a zettabyte is 10 to the 21 bytes. It's yeah, beyond the exabyte, if you like. So when we talk about the SKA as a big data machine, it's really big. I mean, it's not just big in terms of astronomy, it's big in terms of science, it's big in terms of commercial data. And it's really going to push the limits of what is possible to do at the moment. It's so big that IBM refers to the SKA not as big data, but as extreme data. So it really is the biggest of the big. And of course, there's a reason for that, right? The volume of data that we take with the SKA is what gives us access to the enhanced parameter space that allows us to conduct the high priority science objectives of the observatory. And that's what the telescope is designed for. Now, for most of those science objectives, we're going to be relying on population analysis. So it's not enough to look at one example of an object. We need to look at populations of objects and use those to build statistical models of particular astrophysical systems. And in order to do that, the SKA is going to detect hundreds of millions of different astrophysical objects or systems. And if we want to use those data to address our science questions, we need to know which ones of those objects are actually the ones we want for a particular science question. So we need to know which ones are examples of known objects. But the other thing we have to be really careful about is that we also have to be able to identify examples of systems that are things that we've never seen before. And for any new observatory, I think it's true historically that the thing that new observatories become most famous for scientifically is always something that was not in the original science plan. So preserving that discovery space for the SKA is going to be really important, because in order to classify all of these objects, to use them in our analysis, we're going to have to do it in an automated fashion, which for many of the science areas involved in the SKA is quite non-standard, right? We still do a lot of by eye classification in astronomy. So to give you an idea of how that compares to historical radio astronomy surveys, here are some of the most famous surveys over the last, I guess, 2 decades. So the VLA surveys, NVSS and FIRST, came out in the 1990s, early 2000s. And those surveys detected about 50 to 100 sources, radio sources per square degree on the sky. The LOFAR 2-meter sky survey that's come out over the last couple of years is detecting, an order of magnitude more sources per square degree, about 1,000 sources per square degree. The ASCAP and MEERKAT telescopes will then take that up by another factor. So you're getting up to thousands of sources to potentially tens of thousands of sources per square degree with the SKA pathfinders, not even with the SKA. We haven't even got to the SKA yet. And at that point, you really have to say, well, how are we going to examine all of these data? So, the traditional method is that you get an expert radio astronomer, or you get a team of PhD students and you sit them down with a bunch of images and you say, what is this? And there are plenty of astronomers out there who spent their PhDs literally eyeballing images and putting them into bins. So if you want to do that, it takes, if you're an expert, about a minute per source typically to say, this is this type of radio galaxy, this is a different type of radio galaxy. And this is a number that my MSc students actually determined empirically by walking around Jodrell Bank with pictures of radio galaxies and asking people to classify them and timing them. Now, obviously, that doesn't scale to tens of thousands of sources, because even in a year of full-time work, if that person did nothing else, they'd only classify about 100,000 sources. So nowhere near where we need to be for the SKA. The extension to that recently has been citizen science. So the Galaxy Zoo project, and in particular, I'm highlighting the Radio Galaxy Zoo project here, has classified 300,000 sources over just over 5 years, using the contributions of 12,000 citizen scientists. Now, for citizen science, you need more than the opinion of 1 or 2 people, because the citizen scientists are less expert, and so you need more people to agree. So you need a consensus of sort of 10 to 20 people per object. So it's a more labor-intensive process. But even so, 300,000 sources over 5.5 years is still not going to cut it for SKA scale surveys. So then you have to look at machine learning options. And the machine learning options look good, right? With a machine learning algorithm, you could classify 100 million sources in about 15 minutes. It's a representative number from some of the classifiers that already exist, which leads many people to say, well, that's the solution. We're just going to use machine learning, and machine learning is going to solve all of our problems. And that's really, I think, what this talk is about, is whether we should trust machine learning to solve our problems. Because I think that saying machine learning will save us is more of a question than a statement. And I like to think of this as if Ron Burgundy was saying it with a question mark on the teleprompter, which is that machine learning will save us. And the reason I'm a little bit skeptical is because a lot of the large commercial applications of machine learning are put together by people like this, who have mottos that I don't think are consistent with scientific practice. So, you know, if you want to move fast and break things, that's fine, but I would much rather that radio astronomy was not broken in the process. And we've already seen the effect of this in other fields, in particular in the medical field, where there's the potential to do a lot of harm. That the biases in AI algorithms have already been causing problems. And this is, you know, aside from all the biases that we see talked about in social algorithms of AI and applications of AI. So, for this talk, I've sort of built things around these 4 points to address why we need to be careful when we use machine learning for big science, if you like. And the first point I'm going to talk about is why the training data we use is really important. The second point is about how we can use existing experiments to build machine learning models for future surveys and whether that's possible. And then I want to talk a bit about what it is when we're doing machine learning, what it is that we're actually doing, what is it that the algorithms actually learn, and how do we verify that they're learning what we think they are. And then my final point, which I'm afraid I won't actually get to answering in this talk because there's not going to be time, but is going to be the question that I leave you with, is how can we quantify the biases and the uncertainty in our results? So I'm not in any way suggesting that we can get rid of all of our biases and all of the uncertainty in our results. That anyone who's dealt with empirical data analysis knows that there will always be bias and always be uncertainties. But the question is, how well can we quantify those parameters? So to start with this first point, which is why our training data matters, I would like to posit the question, or posit the statement that for machine learning, the data matters more than the algorithm. And I think this is true. I think the data is always more important than the algorithm. So we can tune our algorithms, we can, you know, set them up in particular ways to achieve certain goals, but with appropriate data, none of that matters. So I would say that the data matters more than the algorithm. And I want to show you some ways in which your choice of data can affect your results, basically. So I'm gonna use a non-radio astronomy example just because I think it's quite nice. So this is a set of images randomly selected from the SDSS catalog. So SDSS, as the astronomers in the audience will know, is probably the most widely used optical catalog in the world. It contains over 1 billion different objects. Now the data is not exactly the same for all of those objects. So those 1.2 billion objects all have photometric data, so they have integrated magnitudes in different bands. There are a subset of them that also have magnitudes from the WISE satellite, so in the mid-infrared, and that's about 100 million out of that billion objects. However, only 3 million or 3.2 million have spectroscopic data. And the spectroscopic data is really what you use for establishing the ground truth about what a particular object is. So if we wanted to create a training data set from SDSS with labels that we were confident in, our training data set would only comprise the spectroscopically labeled data. So the question that we posed when we were looking at this data is, can we use the spectroscopically labeled data to label the photometrically observed objects? So can we use those 3 million spectroscopic objects to classify the 1 billion photometric objects? And how we did that is not really the focus of these slides, but just to show you some of the results from that work, just because I think it's really pretty. So Alex Clark, who led this work, he used a parameter reduction method called UMAP, which is a more statistically robust version of the TSNE parameter space reduction that you might be familiar with. And this was our separation of classes. So you can see in green the galaxies, in red the quasars, and in blue the stars. And what you're really looking for is spatial separation between those classes here. Now, to do this, this is just showing the spectroscopic data. So we know the ground truth labels for these objects, and we can assess how well the algorithm does when we apply certain cuts to our training data. So that's what I wanted to talk about. Now, the way we assess the performance of our algorithm is described by, I think I should just skip here, it's described by some parameters which in machine learning terms are called precision and recall. Now, these are the definitions of them, but you can think of them as precision is basically the percentage of your results that are relevant to the question, and the recall is the percentage of the relevant results that are correctly classified. And I know that that sounds very blurry and semantic-like, but basically, if these numbers are higher, the results are better, is what you're looking for. And in fact, we tend not to just use precision and recall separately. We also combine them. We take the mean of these two quantities, and we call that the F1 score, which is sort of an average goodness of model performance. So I'm going to refer to these parameters in the next couple of slides, but you don't need to remember exactly what they are. You just need to remember that the larger the value is, the better it is. And so just to give you a bit more detail on the data that we used, of those 3.2 million labeled objects, so they're labeled as star, galaxy, and quasar, just as in that image I showed you, the majority of those objects are galaxies. So about 70% of the data are galaxies, and only 12% are quasars and 17% are stars. Now, this is what's referred to as class imbalance in machine learning terms. And it means that the algorithm is going to be more likely to classify things as galaxies if we're not careful about how we assess whether it's training properly. The best way I find to think of this is for a binary classification problem. So say we were only classifying galaxies and stars, and our training data was 99% made up of galaxies and 1% made up of stars. If the algorithm simply labeled everything as a galaxy, it would still be 99% correct, but we would not know which ones the stars were. So the result would be useless, even though it looked on face value to be highly accurate. So this kind of class imbalance is going to affect the performance of whatever machine learning model we choose to use. If I just flick through. And the thing about astronomy data that makes this really tricky is that if we take cuts in the data based on different brightnesses of the objects in our catalogue, then we will be cutting uneven proportions of our classes. So, for example, our galaxies may be much fainter than our quasars. And so if we take a low brightness cut, we'll end up with proportionally more galaxies again than quasars. And so we can change the proportion of different objects in our training data by taking cuts at different sensitivities. And this plot is showing you what happens to the performance of our algorithm if we make different cuts. Now, again, the parameters on the left-hand side, the F1, recall, and precision, those are our metrics, performance metrics for machine learning. But again, the main thing to remember is that the higher those values are, the better things are. Now, these plots are quite complicated, but what I want you to see is if we look at the quasars in the central plot, if we cut the training data to exclude proportions of the data below a given magnitude, then the shape of the curve changes. So you can see that the different colors represent different magnitude cuts. And depending on the cut, the shape of the curve changes. So it's not a linear progression. It's not that if we exclude some of the data, then we just get, a proportionately worse performance. We get to the point where we go from 19.5 to 19 in magnitude, and we get a huge jump compared to previous jumps. So there's a non-linear relationship between the sensitivity of our training data and the performance against our test data. Now, the reason I'm emphasizing this is because when we perform a new survey, say with the SKA or any other telescope, typically in our new survey, we will be achieving a greater sensitivity than we do in our old survey, which we're using to make our training data set. So it raises the question, how can we predict the performance of our machine learning model on a new survey when we only have the old surveys to use as training data? So that's my first point, the first way we can bias our results. The other question that comes up when we're looking at bias is that class imbalance. So because there are so many galaxies in our training data, we could just discard some of the galaxies so that we have equal proportions of galaxies, quasars, and stars in the data. But if we do that, what it means is that our training data doesn't have the same proportions of the different objects in it as our test data set does. So our training data becomes less representative of our test data. And in fact, for the SDSS machine learning model, what we see is shown in this top plot here, which is that if we artificially balance our training data, then the performance against the test data is worse than if we use the unbalanced training data set. The other question is, how much of our training data do we need to use? So, 3.2 million objects is quite a lot of data, right? Do we actually need to use all of those training data? And the reason that we might consider this is that training machine learning models is computationally very expensive. And so the smaller the training set you can get away with, the better. So for SDSS classification, what we discovered was that you really only need about 30% of this full spectroscopically labeled data before your performance just doesn't get much better. So you can get away with not using all of the data that you have available to you. However, then that raises another question, which is, if you only need 30% of the data, which 30% should you use? Now, typically what people do, if they're faced with a classification problem, say we're trying to separate the blue population of dots from the red population of dots, is that you'll randomly select a set of training data to train your model. So for example, we might randomly select the points that are circled in black here. However, not all of these points contain an equal amount of information about the division between those two classes. In fact, if we wanted to choose points that contain the most information about the division between those two classes, we'd really want to choose the points that lay along the boundary. So this kind of data selection for training is called active learning. And you can see the difference in performance between randomly sampling in orange on the right-hand side and sampling along the boundary there. It's called uncertainty sampling in blue in the right-hand plot. So again, whichever line is highest has the higher performance. And you can see that the uncertainty sampling gives significantly better performance than just randomly sampling our training data. However, whilst this is very clear cut for a two-class classification problem where we can just draw that dashed line and say, what's the probability of a point line near that line, it becomes more complicated for something that has, say, three classes like SDSS. So in this case, we might have stars, galaxies, and quasars in red, green, blue. And deciding how to sample these data to identify those boundaries becomes somewhat more complicated. However, it is doable. And again, you can see on the right-hand side that for different mechanisms of active learning, which is what the different colored lines represent, you can get a significant difference in performance by choosing a particular method of selecting your training data. So I think, yeah, so this is my first point, is that how you select your training data really affects your results. And although I've talked a bit about SDSS, I think maybe it's time to move on to radio astronomy, since that's primarily what I like to look at. So here's an image of the Meerkat first light field. So this is one of the earliest images from the Meerkat telescope, and you can see that there are lots of different objects in there. For the non-radio astronomers in the audience, basically every bright point in this image is a supermassive black hole. And if we zoom in, we can pick out the morphologies associated with some of them. And you can see immediately that they're not all the same. So these are different types of radio galaxy. And radio astronomers tend to divide these into Phaneroff-Reilly class 1 galaxies and Phaneroff-Reilly class 2 galaxies. It's the most common morphological classification of radio galaxies. And it refers to the difference between the host of the galaxy, where the supermassive black hole is, and then the morphology of these outflows, which tend to be sort of symmetric around that host region. And so a lot of work has gone into classifying radio galaxies. And because this is a morphological classification, this work has primarily been done using convolutional neural networks. And I'm not going to talk about how convolutional neural networks work, so I apologize. If anyone wants to ask questions, they can do. But to give you an idea of the scale of the machine learning problem for convolutional neural networks, they're called deep learning because they contain a very large number of learnable, i.e. trainable parameters. So some of the work that's been done to classify radio galaxies using convolutional neural networks has used networks that have, over 100 million trainable parameters to do their morphological classification. And that's fine if you have millions of images to train your data on. But in fact, the number of labeled images in radio astronomy is quite small when you consider the fact that your labeling has to have been done in a consistent way across your training set. So in fact, reducing the size of these convolutional neural networks to give equivalent performance has become something of a common practice in radio astronomy. And through these 3 different papers here, you can see that you get comparable performance from different networks if you reduce the number of trainable parameters down from 100 million to only a couple of 100,000. And in fact, in one of our more recent networks, we're now getting equivalent accuracies with less than half of the smallest network here, so less than 100,000 parameters. And this has become a really common thing to do. So lots of people are putting together convolutional neural networks to classify radio galaxies. This is a schematic of the Claren classification network, which was put together for the Radio Galaxy Zoo, or trained on the Radio Galaxy Zoo catalogue. However, what you do tend to notice is what I've put in the box with the references at the top right here. So I've put the reference, and then in brackets, I've put the name of the survey that the classifier was trained on. And what you'll notice is that a lot of these surveys are all trained on the first, a lot of these classifiers are all trained on the first survey. So that's the VLA radio survey. And they're trained on that survey, and then they're evaluated on that survey. Now, the reason I bring this up is because when you do that, what you are doing, when you present your performance metrics, when you say my model is 90% accurate, you're not saying that this model will always have an accuracy of 90%. You're saying that on the first survey images, it has an accuracy of 90%. And again, going into the era of new radio surveys, I think that's the wrong question to ask. So the question we should be asking is if I train my model on data from the first survey, will it work on the Meerkat Mighty or the ASCAP Emu survey? So this brings me to the question of, can we actually transfer knowledge from existing surveys to new surveys? And this is a process that's known as transfer learning in machine learning terms. And there are different ways of doing it. So specifically with convolutional neural networks, you can transfer information from different parts of your network. So in a convolutional neural network, the convolutional layers are effectively extracting feature data from your images. And then the fully connected layers at the end are doing the classification. So you can think of the first part of the network as producing the information that goes into the classifier, although both are trained at the same time. So you can do transfer learning by freezing the convolutional layer parameters, so you extract the same features for any image that you put into it, or you can freeze the fully connected layers, or you can freeze both. So you could train on the first survey and then freeze your network and apply it to the EMU survey or the Mighty survey, or you could use that frozen model as a new starting point to retrain your overall model. So all of these are options, so it's not a completely, hopeless question. However, again, we do need to be a bit careful about introducing biases. So one of the things that my PhD student Hongming Tang looked at was, can we train a machine learning model on, say, the first survey and then apply it to the NBSS survey? Now, the NBSS survey and the first survey are both observed with the same instrument, but in different configurations. So they have different resolution. And even more importantly, for radio interferometers, it's not just the resolution that's important, it's the range of spatial scales. So it's not just that there's a smallest spatial scale that they're sensitive to, but there's also a largest spatial scale that they're sensitive to. And that's what I'm showing in the figure on the right here. These are the range of spatial scales that are measured by different surveys. So you can see first an NBSS in red and blue there, and then ASCAP, Meerkat, and SKA1 mid is the dashed lines. And the question that we were asking is, if you train a model on a survey with a particular range of spatial scales, can it be transferred to a different survey? And the answer is yes, sometimes. So on the left-hand side, I'm showing the different, so this is called a receiver operator characteristic curve, or a ROC curve, which shows the true positive rates against the false positive rates for our model applied to our training, to our test data. And basically, for a good model giving good performance, you would expect the line to shoot up, much like the red line on the bottom plot does, and get as close to 1 and stay there as possible. And that's the optimal model. And you can see that on the top plot, the two lines are pretty much the same. Now, this is a model that is trained on the NBSS survey and then tested against NBSS and FIRST, and it gives similar performance. But on the bottom is a model that was trained on the first survey and then applied to NBSS and FIRST. And you can see that for the red line, which is the first data, it's doing a good job, as you might expect. But for the NBSS survey, we've got a pretty much diagonal line. And that is basically random guessing. So even though it's a fully trained model that works really well on the survey it was trained on, it doesn't know anything about the NBSS data. It can't classify the images from the NBSS survey. And that's because of the difference in the spatial scales. So we have to be a bit cautious when we say that we have trained models on existing surveys, because it's not necessarily true that those models will work on new surveys. So whilst that is potentially catastrophic if they don't work at all, it's almost worse if they do work or appear to work, but their performance is not what we thought it was. because that kind of bias is very difficult to identify, and is another potential source of error. I'm just going to skip this one, and I'm going to move on to my third and final point, which is, how do we know what it is that the machine learning models are actually learning about our data, especially when we're talking about convolutional neural networks, where it's very difficult to understand what's happening within the network itself. And there's an example that I really like, that one of my PhD students showed me, which is a lot of online image classifiers, so things like Google image search. If you show them a picture like this, they will tell you that it's a sheep, even though there's no sheep in the image. And the reason that they think that this is a sheep is because when someone trained the classifiers that underlie those algorithms, all the images that they showed them of sheep were images of sheep standing in fields. And so the classifier learnt not that the sheep in the image was the sheep, it learnt that the field was the sheep. So we have to be quite careful to make sure that the classifier is actually focusing on the object of interest in the image rather than the surroundings or something else that would commonly appear in the same image. And so one of the ways of doing this is to use a property called attention, which is a way of correlating the intermediate stages of convolutional neural networks with their classifications. And this is something that gets used in, or has been used in medical imaging, for example. So this is from a paper which I think is called How to Find the Pancreas. And it's looking at MRI images. So the input on the left are the gray images, and then the network is being progressively trained from left to right. So you can think of the network becoming more and more confident as we go from left to right in the images. And what you can see is that the heat map over the image is really isolating particular areas, and it's focusing in on specific organs, which is what the algorithm has been trained to do. And so when it says, you know, the pancreas is enlarged, or something like that, then you can look at these images to check that it has actually been focusing on the pancreas. So the same is possible for radio astronomy images. So again, this is something that one of my PhD students is currently PhD student, what did this as his MSc work, has been looking at, is about understanding what it is that convolutional neural networks are looking at in our radio astronomy images when they say this is an FR1 type radio galaxy or this is an FR2 type radio galaxy. And you can see on the right hand side, this is an example of not the greatest radio galaxy in the world, but an FR1 type radio galaxy in the black and white image at the top. And then the image at the bottom is showing the distribution of attention that the network is looking at in the image. So basically where you can see structure in the bottom image, that's the information that the network is using to classify this source. And this gives you a really nice visual representation of how classifiers are working. And in particular, when we look at FR1s versus FR2s in radio galaxy images, we can see that the classifier focuses on the center for FR1s and focuses on the more extended structure for FR2s, which is what we as radio astronomers would tend to do. So the final point I want to make on this subject about what it is that we're actually learning is that if we know what we're learning, then we can reproduce it. So to give you an example of why this is important, the Scafe organization has been launching a number of science data challenges to try and engage the community in using the data ahead of the telescope, because it's going to be a different experience with such large data sets. And so to do this, they've been simulating fake radio skies, if you like. But it turns out that simulating radio galaxies is actually quite complicated, because radio galaxies have, these diverse morphologies that are difficult to classify and even more difficult to reproduce, unless you want to make a full magnetohydrodynamic model, which takes forever to do and only gives you one radio galaxy at the end. And so, in fact, a lot of the simulated sources we see in these fake radio skies are simply Gaussians. So they're not particularly realistic at all. So the question arises, if we understand how the machine learning is classifying radio galaxies, can we use machine learning to generate new radio galaxies or generate images of new radio galaxies? And this is not something that's particular to astronomy. So in this set of images, so these 8 faces in front of you, none of these people exist. So all of these images were produced by a machine learning algorithm that was trained on a set of data and asked to produce a new face. And you can go and do this yourself. You can go to the website thispersondoesnotexist.com and generate a machine learning generated face. But the point is that if it's possible for faces, it's probably possible for radio galaxies. And this form of machine learning is known as generative machine learning. So instead of discriminating between different inputs, what we're doing is we're using those distributions of discriminative inputs to generate new examples of a particular class or a particular type of object. So this is work that my MSc student, David Bastian, has been doing, using what's called a variational autoencoder to basically compress the information in images of radio galaxies into a lower dimensional latent space, and then to resample from that latent space to produce a new image. So the typical example that you see of this is with handwritten numbers. So if we train one of these encoders to reduce handwritten digits into a latent space, we might get a latent space that looks something like this distribution of numbers you can see in the square at the bottom here. And if we pick a point out of this square and pass it through a decoder, we can produce a new handwritten digit. And if you can do it for numbers, you can also do it for radio galaxies. So I apologize to David because these images are a bit old, but I really like this. So in this image, there are 26 postage stamps of radio galaxies that David produced using his variational autoencoder. 13 of them are real radio galaxies, and 13 of them are fake radio galaxies that were produced by the AI. And you can have a guess which ones are real and which ones are fake. I'll show you in a second which ones are fake. But just looking at them, I think it's actually extremely difficult to tell the difference, even for an expert radio astronomer. So if everyone's peered at them a little bit to try and decide which ones they think are real and which ones are fake. These ones are the fake ones. I'll just flip back. So I think a lot of people look at number 17 and say, oh, that has to be fake because it's so linear. But in fact, that's one of the real ones. And these are the fake ones. So for producing simulated SKA skies, so fake radio surveys, David's algorithm is now being integrated into that process with the Scaife organization. Which brings me back to those 4 points that I put up originally. I'm not going to talk about number 4, but hopefully at this point you're feeling pretty confident that it is an important question. And if you're using machine learning yourself, you might want to consider it. And I'll just close by saying, isn't it fantastic what we can do with AI in radio astronomy these days. Thank you very much.
Thanks very much, Anna. That was very illuminating, and I certainly learned a lot myself during that, and probably wish I'd heard that talk before trying to embark on supervising Vivian on a project similar to this, which you helped a lot with, which was very generous of you as well. Okay. So don't forget anyone to put a question in the Q&A box. Any thoughts or any questions at all on what you've heard, or anything coming out of it related to it, anything you like. While people are thinking about that, I'll ask a question myself. As well as someone who is currently spending my evenings doing visual classification of thousands of objects, mainly for my own edification, but also I know that it is being used as a training set already. So you talked about finding new types of sources, like the sort of unknown sources in the SKA surveys. Now, obviously, all of the training, in a sense, and labeling is on known types of sources. I mean, I guess we always have a category of other or something, and we don't quite know what it is ourselves. I certainly do in my survey, but they're a bit of a mishmash. So how do you see that sort of working, in a sense? I mean, it's the ultimate bias that you might only ever study what you already know, because all your training sets are on things you already know, obviously. You're muted, I think.
Yeah, sorry, maybe I didn't. Yeah, so I think it's a real risk, is the answer. So if you're classifying, I don't know, 100,000 objects or 10 million objects, and there are 5 really, really interesting things in there that no one's seen before, how do you pick them out? Because the risk is that they will be classified as one of the known types of object. And with that volume of data, it's very difficult to sift through and find them in any manual manner. So there are ways to address it. So in terms of general classification, there is this other class, if you like. So this would be a variant of one class classification where you have an undefined class included in your model, but it's how individual models perform in that situation is very difficult to predict. My personal feeling for how we're going to address this is actually to look at the model uncertainty on the classification of individual objects. So there are 2 types of uncertainty that come into classification, and regression as well. I tend to talk about classification more typically, but there's the uncertainty inherent in the data samples. So what's referred to as aleatoric uncertainty. So some images are clearer than others. Some images have contaminating sources, which affect the uncertainty associated with a particular data sample, and that's an irreducible form of uncertainty. But then there's also the uncertainty that's associated with the model itself, the epistemic uncertainty. And I suspect that the properly calibrated epistemic uncertainties associated with classification probabilities will be able to identify unseen sources, because if something is unusual, it should not conform to one of the known classes in some way, in which case the model should not be certain in classifying it. So being able to correctly quantify that uncertainty is important, and it's actually a whole other talk, because how you do that, particularly with neural networks, is a relatively new area. Most neural networks are inherently frequentist. They don't give you uncertainties on their classifications.
Yeah, I mean, I guess I was also thinking maybe along the lines of more of the unsupervised learning type of things where it just, I mean, maybe those don't work on images, I don't know, but.
Well, no, so you can, yeah, so you can do unsupervised learning. And I think that, I think the thing that we're more likely to see from unsupervised learning is a challenge to our existing paradigms of classification rather than looking necessarily for new things. So for example, FR1 and FR2 type radio galaxies is it's a subjective cut on the morphological characteristics, and there is no clear distinction, right? It is a spectrum. So I suspect that unsupervised machine learning might give us a different morphological classification.
Yeah. Okay. We have some questions in the Q&A box now. First one's from it's been sent in anonymously, so unless someone owns up, I can't ask them to come on the mic and ask the question. And it's quite long. Maybe, Anna, if you can see it in the Q&A box, maybe if you want to.
No, so the question is about reproducibility. It's a good question. There is this tendency for people to consider machine learning algorithms to be black boxes. So my MSc student David, who's listening in, will know that I particularly object to the term black box for machine learning algorithms. All machine learning algorithms are understandable, and people tend to refer to them as black boxes either because they don't have the time to work out or the background to work out how they actually operate. But you can certainly quantify the operation of machine learning models in many different ways, and the maths is completely tractable. However, understanding how they work does not necessarily allow you to reproduce someone else's results. And I completely agree that this is a problem. So reproducibility, I think, firstly, you need standardized data sets that are publicly available. You also need to share the models, the trained models, I think, as well as the hyperparameters. One thing that I notice from a lot of computer science papers on machine learning techniques is that people are quite, I don't know, it would be wrong to say lazy, but people often, what's in the paper does not match what's in the code. And so it is very difficult to know what's going on. So I think consistency is what we should strive for. Make the data public, make the model public, and be as clear as possible in the paper about how something was done. And ultimately, the other thing which I also push for is making the environment public. So making a containerized environment where you ran your code public as well. And then those three things should give anyone the opportunity to reproduce your results. And the resources are starting to be available. So GitHub is one resource, Singularity Hub and Docker Hub for environments, and then you can link everything together on Zenodo. So I really, if you're not familiar with those tools, I do really encourage people to have a look at them.
I'm going to get on to another of your favorite topics of open science, I suspect.
I would say, so yeah, the question is, doesn't this threaten the integrity of science? I would say that something that is reproducible is not, something that isn't reproducible is not science.
Yeah, that's a good answer. Solomon, always a banker for asking the question, and yeah, sorry you joined late, and I can ask it for you if you like. No, Anna didn't really mention it, I don't think, which was, I mean, you said these are computationally intensive. And this is a bit of a how long's a piece of string type of question, really, but I guess Solomon's really asking how computationally intensive, you know, what sort of, how many hours and hours and hours does it take to train these things?
Yeah, and the answer is it depends what you're doing. So for a simple network like, let's see, sorry, I'm just flicking through my slides to give an example. Okay, so for this network with 250,000 parameters, you can train it in minutes to hours on a CPU, in fact. When you start to get up to millions of parameters or millions of data samples, then you need to go onto a GPU if you want to see anything within a day. For something like David's models that have both an encoder and a decoder, those are huge, and the number of trainable parameters is enormous. So I think that David had training runs that ran for a week on a GPU. So you would need to scale your computational resources to the problem. However, if you're just about to get started and you want to try out some test things, then a simple network, even simple convolutional neural networks with standard data sets like the handwritten digits data sets, you can run those on your laptop in a matter of minutes. Yeah,
yeah, that's very useful, Anna. And yeah, so I mean, Vivian from Kenya, who was just doing her master's on CNN classification of the topic objects. I mean, we were getting more complicated, I guess, in a sense that we weren't just using the radio data, but we were using multi-wavelength data. We're using mid-infrared and near-infrared and data as well, and because that's really what you need in order to classify the galactic sources, because you've got many different, they're not all, there were radio galaxies in there, but we had lots of different types of nebulae and everything. And so she was up to 48 hours on a frontline GPU cluster, which was generously donated by the Goon-Hilly collaborators. So that's kind of where she got up to. And even then, the results were still a long way from where we need to be, really. So, okay. Another anonymous one. So let me ask you that one too. So what about machine learning on radio astronomy data cubes? Is it possible, and how computationally intensive would it be?
So this is something that I haven't seen done yet, but it's definitely going to be the next thing on the horizon. So I mean, for typical image classification using convolutional neural networks that just use, like, I don't know, cat or dog pictures, right? Those pictures themselves are RGB images, so they have 3 spectral channels in them. Whereas for most radio astronomy classification, we just use the grayscale images at the moment, which is 1 channel. So already, we're not using as much information as even simple photograph classification. And for radio astronomy, there's so much information in the spectral domain, be that frequency or velocity or Faraday depth is the one that I'm particularly interested in. So there's a huge amount of potential there, and the algorithms are set up for it. So the algorithms are set up to take in multi-channel data samples, so cubes are no problem. Large numbers of channels are going to make it very computationally intensive, though. You would scale the weights in the number of weights in the first layer by the number of channels, and that would be huge for something like a 1024 channel cube, or if you wanted to go up to like 64,000 spectral channels for SKA, right? It's crazy. That I don't think would be possible. However, if you wanted to include, say, Stokes I and spectral index, or a few samples across a spectral band or across a spectral line, I think that would definitely be doable. The main problem at the moment is having data sets that are put together in a systematic way that have that spectral information. And actually, so Vivian's project was an example of this in a slightly different way. So I mean, Vivian used multiple frequencies, and those could be considered, they're sort of a proxy to a spectral cube, if you like. So that it's so it is being done. Yeah. Although you'd probably call that a multi-messenger rather than multi-channel, I would guess.
But yeah, she did code it up as basically 5 channels in a cube. So, so that, it's not what we normally think of as a data cube, but no, that's a really interesting idea as well. And I guess we need Moore's law to keep going in GPUs as well. Otherwise, we're not going to get very far. Yeah. Just coming back myself to what well, another point you raised about the kind of the transfer learning, I guess, as you're calling it. I mean, you were, you gave the example of training on NVSS and trying to apply it to the first data, so there's quite a big resolution difference there, and it basically didn't work. Could you also, in a sense, I mean, if you've got new survey data coming in from the SKA, previous machine learning algorithms that have been tested will have produced labels for all of these sources, and obviously you can then locate those sources in the new imaging survey data. So you could transfer the labels and then start again, couldn't you?
So yes, if there's overlap is the answer.
Yeah.
One of the biggest issues the SKA is going to face is that most of its survey area will not overlap with most of the existing radio surveys because they're in the Northern Hemisphere. For extragalactic sources, it's going to be, so NVSS and FIRST barely go below declination 0. So that's practically half the hemisphere is not labeled. So then you'd be limited to surveys that had been done in the south at comparable frequencies. So you'd be looking at something like sums or anything that had been done with a compact array. And the resolution difference between Molonglo and Meerkat or ASCAP is huge, right? Also,
we'll have had 5 years of Meerkat surveys.
Yeah, so yes, so Meerkat could be used for SKA, but the question is, what do you use for Meerkat?
Yeah.
Yeah, that is true.
Yep. Well, I've got at least 3,000 radio galaxies in my galactic plane survey, all at slightly higher resolution than Meerkat. But I mean, I think going from higher to lower is better than the other way around, isn't it? I think that's what you learned from FIRST and NVSS.
No, so in fact, it was the other way around for FIRST.
Oh, right.
Yeah, so the high resolution FIRST images couldn't help you classify NVSS.
Ah.
And we've been seeing this recently, actually, when we've been looking at giant radio galaxies across different observation frequencies. So it's, yeah, and again, it comes back to what is it that the algorithm is actually learning. Yeah.
Okay.
Yeah.
So Solomon's got another question there. Are these algorithms available to the general public, students, to do radio astronomy research? How can they be accessed? Any specific skills required?
So if you can write Python code, you can run AI, is the reality. So there are all kinds of nice libraries to help you out with getting started in AI and machine learning in Python. So for convolutional neural networks, we tend to use the Pytorch library. So there's a temptation for everyone to try and use TensorFlow immediately, but TensorFlow requires very, very careful tuning of everything. It's not a very friendly library, and then people tend to move from TensorFlow to Keras to try and make it a bit easier. But Keras is also a bit odd in some senses, and then eventually you get to Pytorch and everything just works. So I recommend Pytorch for convolutional neural networks, and for things like random forests or SVMs, the scikit-learn library is very good. Pytorch also, it's very easy to run code on a GPU using Pytorch directly from Python. If the GPU is there and available for you, you don't have to do anything special. You just have to tell Pytorch to use the GPU. So that's the other, it's a really low entry point to get onto GPUs using Pytorch. Yeah. And then I think, so in principle, all the algorithms are available, and the other key thing that's becoming available are the data sets. So the data sets that my group use, we're making publicly available. So some of them are already up on GitHub, and lots of people use them, like non-astronomers use them for machine learning ones. We have a pulsar data set from the high time resolution universe survey that's been used thousands of times by I don't know who. I just see when they download it from GitHub. And so yeah, so there's lots of resources.
Must be people who still think pulsars are really aliens, probably.
You think they'll have a hard job proving that with our data set.
Okay, sorry, the questions are scrolling off the bottom here. Dennis, he's got a question about when an algorithm is trying to work on a particular survey, produces good results. Well, it's similar to what we were just talking about, really. What adjustments do you need to make sure it works on the other surveys?
Yeah, so it's going to depend on how widely different the surveys are. So typically, if you train a model, it will generally work on a different set of data. The question is how well it works. And really for that, you need to have enough data from the new survey, enough labeled data to be able to validate the performance. And once you can validate the performance, then you can start retraining certain aspects of the algorithm. So sometimes it will simply be a case of, taking the existing model as your starting point and refining the trained values. In more complicated cases, you might have to change the architecture of the algorithm. So you might need additional convolutional layers to extract different features, or you might need more depth in your classifier. If you have a subclassification, like a hierarchical classification problem, then you may need to address the way that you're actually doing your classification, because that's very difficult, especially if you have very small numbers of individual subgroups of classes. And there's some nice papers on this for variable star classification, where you do see these hierarchical classification structures by Zafira Hosseini, addressing how you can get good performance out of those kinds of surveys.
Okay, I think we've exhausted the questions. Thanks again, everyone, for asking some.
Yeah, hand up, Melvin.
Sorry, there's hands up. Oh, well, I wasn't looking at that bit either. What have we got? Sigrid. Okay. Sigrid, do you want to? I can allow you to talk, and you can ask a question.
Wow, thank you very much for the presentation. Wow, this is high level of understanding astronomy, actually, but I just hope the question that I'm going to ask makes sense, actually. On your slide of basically explaining the data percentage that we can use in terms of data for training and to the active learning. Yes. Oh, sorry.
Is that the right one? That's the slide, or these ones?
Yeah, well, I think the model, yeah, well, some of these models I think make more sense to me. But I just wanted to understand or ask, why is it only 30%? Yeah, I don't know if you answer it within your presentation, but I didn't get it.
Yeah, so at 30%, so if so there were two things. So it's a good question, and I didn't go into it in detail because I didn't think I had time. So thank you for the question. So in the plot here, I'm increasing the fraction of the training data set, and this line is at 60%, but it's 60% of half of the 3.2 million objects, so 30% of the full sample. And what we saw is that for fractions higher than this, basically the gray line doesn't change. So we have no further improvement in performance, even if we go up to 100%. So the performance using all of the data is the same as the performance if we use only 30% of the data. So that's the first thing, which is telling us that there's no new information. Like we've seen all of the salient features within the data by the time we've sampled 30% of the data set. The other thing that we were looking for is the linearity of these lines. So these are the subclasses, if you like. So you can see at low fractions, there's quite a curve to these lines, and it's pretty much curved until you hit this same point. And that curvature is due to the class imbalance. So what we're seeing is a difference in performance that depends on the class. So a class-specific performance change, because the gradient is not the same for all three classes. And that stops at this point as well. So after this point, we've seen enough examples of each class not to be affected by the class imbalance so much. So that linearity is the other thing that we looked for. Does that answer your question?
Yes, it really does, because I was really looking at it on this point, the models, instead of this one.
Yeah, so I went through this really quickly, but the paper is available. So I do, if you're interested in this, I think Alex did a really good job on trying to decide how much data was enough.
Okay, great. Another question, sorry.
Yeah, go ahead.
If training data have a greater effect on our results in terms of analyzing things, how can we then better this? How can we improve it? Because I know in AI it's just as unbiased as data inputted.
Yeah, exactly. I mean, the models learn what we show them is the reality, and one of the things that you have to remember about machine learning models and how they view data is that they have no additional context. So I was listening to a talk once where someone made a great comment that I think so Google Linnet, which is one of the most high performing deep learning architectures, is trained on something like 13 million images, or 13 billion, I forget. It's a very large number basically. And the guy who was giving the talk was saying that that's the same number of images that his 7-year-old son has seen in his lifetime, roughly. So he'd done this calculation. And he said, but if I show my son a crayon drawing of a cat, he can tell me it's a cat, whereas Google Linnet can't tell me it's a cat. And the difference is the context. So we have to remember that the models can only understand what we've shown them and have no wider context at all. And so any bias that we introduce into that training data will be replicated by the model, and potentially will be amplified by the model because it will learn the bias and think that it's intentional. So I don't think we'll ever remove that completely, because I think it's way too optimistic to imagine that we could produce an unbiased training set. However, what we can do is quantify it, and certainly in astronomy, the quantification of selection biases is something that's already inherent in a lot of our analysis, because by their very nature, astronomical observatories introduce selection biases. And astronomy is a science where you can never control the experiment, right? You are always the observer and you can never change the setup. So there's a lot of work in astronomy already on selection biases, and I think we just have to integrate that into our work on constructing training data sets and understand how it influences the results.
Wow, thank you.
Great, thanks for those questions, Sigrid. Thanks everyone for your questions. I think we should wrap it up there. So just remains me to thank Anna once again. That was an excellent talk. I hope those of you who are a bit like me, sort of unfamiliar with this field or just dipping your toes into it, learned a lot. I certainly did. And even those, I know many of you are already very familiar with this topic. But hopefully everyone got something from that. And it, you know, it's a field that is being applied to pretty much everything in our human existence at the moment.
Yeah.
And I think, you know, another point that obviously Anna likes to make a lot is, you know, the skills that you get from applying AI in the astronomy realm, where we're sort of primarily interested at the moment, you know, can be applied to many other spheres to attack all sorts of problems, development problems, and just the basic idea of going out and making some money. So many thanks, Anna. That was excellent.
Welcome.
So, no worries. So the final one of the year will be, we've got another one coming up on the 9th of December at, again, the usual time of 1700 hours UT. That's going to be the second part of Peter Wilkinson's talk about his tabletop radio telescope, so another one from Manchester. So where he's actually going to sort of, you know, demonstrate during the talk, I think, how the telescope actually is used to take data. So again, this is the tabletop telescope that's going to be shipped out to our partner institutions in Africa for, you know, so that people can get some actual hands-on experience at some basic radio astronomy. So hopefully people will tune in for that one, the last one of this year. Okay, so thanks everyone, and we'll leave it there for now. Thanks everybody.
Thank you. Cheers.
Yeah, thanks again, Anna. I need to head off now, so I'll get going.
No worries. Cheers, Melvin.
Cheers.